My recommendation is to just don't watch the teams ones unless it does. Usually there's about a day lag for me to post the ones up on the YouTube. Or basically, when I say YouTube, what I say is on Canvas, you will see the lectures posted. If you go on, there's a page, a lecture page. If you go to the page, you can play the lecture. The lectures right now I've got them on YouTube, or I could embed them as well from the My Media, but that wasn't working the first week of class. Okay, does that make sense to people?
Yeah, I think the YouTube ones are fine. So overall, I've watched one or two of them, and I think that they've been pretty good. So I would say that you're doing fine with those.
Yeah, I just don't want anybody to be handicapped here. The Teams is kind of a backup, but the Teams videos do have all the stuff that we're talking about in class. I edit that out of the YouTube ones. Okay, so let me just show you this. This is the schedule. So the first exam is the week of October 18th.
The week of, okay,
So I'm
gotcha.
looking at my date here, right? So the Tuesday after October 18th. So what date is that?
That's the 20th.
20th. October 20th is our date for the first exam. The second exam is the week of November 15th. So it's pretty well spaced. It's pretty good this semester. Everything is almost on track. We're right here in this week, and it's Tuesday. If we can finish our lecture on Module 2 today, we'll really be on track. I'm going to have to start on that. But okay, if there's no more questions, I'm going to go to the...
I just have one quick question, just for clarification for that exam time. Do we have a lecture hall picked out for that? Like, is it going to be available to everybody? It's not going to just be like one group or some weird
everybody at once
workaround. Okay,
it's got enough room for everybody. Pardon?
Okay.
At the normal lecture time or at a different time?
It will be at the normal lecture time, during lecture time. And it will be in EMS. It's one of those two big rooms on the first floor.
Oh, over by the grind?
Yeah.
Okay.
Yep.
Sounds good.
Those rooms have enough space for everybody.
All right,
okay.
Cool. Thank you.
So I think all is cool there. And, okay. So let's go into this. I want to take a quick review of something. Really what we have done, so what we did in our last lecture, just to remind everybody, is we talked about Faraday's law. Faraday's law, from flux linkage, we were able to derive inductance. And so a quick summary of what we got here from Faraday's law, and then I'm going to go into some examples. Is that we ended up really with this expression. We started with the very complicated Maxwell's equation here. Where you do a line integral of the E field over a closed contour. That line integral is equal to the derivative, the negative of the derivative of the flux, which is the integral over a surface area of B dot ds. Now this simplifies greatly down to, on the left-hand side of the expression, a voltage or an induced voltage, and we called that EMF, electromotive force. being equal to the time derivative of a flux linkage, which has this expression. And if in fact the voltage is a non-zero, then the flux linkage would have to have a time dependency. So what is the flux linkage? Really what it is, I went through it in detail last time, but it is the linkage of the flux into the turns of a coil. So if you have a flux in a core, you're going to link that flux into so many turns. And I kind of tried to describe what that meant in terms of Faraday's law, which I'm not going to repeat this time. But essentially, what you have is the turns of the coil, and this is the flux, which has a time dependency. If it may or may not, so I'm writing it this way with the times dependency, and I'm going to take a little discussion on symbols for a short moment here. So we have the flux into the coil. Whatever flux is going into the coil. Now we may also have a, let's call it a time invariant flux linkage, meaning that there's no variation with time. That is highly possible. For example, DC. So you've got a DC current. You can have a DC current. You can still have a flux linkage. You can still have an inductance. And in that case, I would write it like this. Lambda is N times flux. And we've used these different symbols for the flux. And we've used the symbol for various versions of what I would call phi. Remember, we used this symbol here. We tended to use this as an angle, right? So that was one version. That's the little phi. We used the version, sometimes I forget to put these little lines across here, but what I'm doing here is I'm using this for flux. Sometimes we might confuse these in the notes, like if you're looking at any of the old notes that I have for the class. I just want to make this distinction. If I accidentally forget to put the two lines across, just remember the context in which we are using this. Are we talking about electrical stuff? Then we're talking about an angle here. If I'm talking about magnetic stuff, I'm talking about a flux. And then in the text, it uses this symbol, but it also uses this symbol here. I'm going to use this if it has a time dependency. So this is another symbol for phi. It's kind of like a script version of phi, kind of like an italicized, I don't know. But if it has a time variation, I'll use that, okay? So the point is that I've got these are really saying the same thing, but this one definitely has a time dependency in it. Okay? Hopefully I haven't confused anybody. Questions on that?
No, that makes sense.
Okay, great. Now what we have introduced, since we have this lambda n times the flux, we can derive inductance from that. So L is equal to whatever your lambda is divided by the current This is the current in the coil of interest. Now, why I'm making a distinction here is because we're going to introduce more than one coil. And this is where we want to kind of keep our P's and Q's in order here and understand what we're doing. Now, we derived last time an inductance. And I'm going to write this down because what you often have is you have a very common scenario is the inductance of a gapped core that is unsaturated. And so here's your gapped core, like this. I'm assuming that I've got the same core area everywhere. So that's the area of the core. Here's your gap length. Sometimes I'll write it as LG. Sometimes it just might be written as G. You've got turns around the core with a current going through it. You have N turns. You have the mean magnetic length in the core, LC. Now the magnetic circuit looks like this, where you've got the reluctance of the core and you've got the reluctance of the gap. But if the permeability, the relative permeability, is approaching infinity, it's an extremely large number, then RC is approximately 0, in which case your magnetic circuit reduces down to just reluctance in the gap. Now this is a common way of just looking at inductors, but it also confuses people sometimes, and students, if you're just memorizing formulas, if you get the wrong formula, you can get screwed up here. If you take the unsaturated core, you have the reluctance of the gap, you've got the applied MMF, N times I, of the coil. And if you want to find the inductance, you would first find the flux. The flux, in this case, is equal to N times I over the reluctance of the gap. The reluctance, which is N times I over the reluctance of the gap, would be the length of the gap over mu naught and the area of the gap. And so you now would have an N-I mu Ag over the gap length. The flux linkage of this is N times, see here I didn't put my little lines across my flux, N times flux, and so that would be N squared I mu Ag Lg. The inductance is the flux linkage divided by the current, so that basically takes this current out of the expression. N squared, this is mu naught, area of the gap, Lg. This is a very common expression for inductance of a gapped core. But it is not a general case, and students often make that mistake. They see this formula, maybe they've seen it somewhere before, and they think, okay, that's the inductance expression. It's only for an unsaturated it's unsaturated as well. Remember that you had neglected the core reluctance to get this expression. So if you want to never go wrong, what you want to do is you want to define the inductance this way. L is equal to N squared over the reluctance, the total reluctance, or the equivalent reluctance of what we're looking at, okay? This is the expression that you want to write down in your little notes for your test, not the other one. Okay, any questions about that? Pretty clear?
Yeah.
Okay, good.
So what do you meant? This is the general one. If we have saturated core or unsaturated core.
That's absolutely right. Yep. That way you're not going to make up a mistake, because if you did the other one, you have an unsaturated core, so you just neglected all of the core reluctance if the core wasn't saturated. And what if you have a very complicated structure, which is what we're going to talk about today. We're going to show you a few of those. So that's exactly right. So let's talk about, in this lecture, we're going to go through some examples. We're going to go through what multiple windings on magnetic circuits and how would you handle that. And then we're going to go into AC excitation. I do think it's important for you to see a few examples. And so let's go through this one first. Again, it's a little bit of a review, but there's a point I want to make on this example here. So what we have is an ungapped core. We've got a current into this winding right here. Now, what you're going to do is often you're going to see situations where you have, what you've got is you've got a path in the core here. So this is the length of the core. The way that you'll often be given dimensions of a core in different ways. There's no one way to do that, and you need to be a little bit flexible about this. This core is, what's given here is a typical way if you go into a data sheet. Sometimes the data sheets, if the core itself is a purchased part, okay, and I'm talking about this thing right here, they may just give you the length, the LC value in the data sheet and not have you calculate it. But sometimes you'll just have the data. So it may be in terms of different variables. So in this case, we have an A variable right here and a B variable that are defining the core area. So the core area, AC, is A times B. They've also given you what's called a winding window dimension. So you got the core dimensions and the winding window dimension that you're going to wrap these coils in. Typically, the coil fills up this whole area. This is space right here that we're talking about. It's filled up with copper as much as you can get in there to try to utilize everything, the space, the size, everything that you have to maximize the utilization of everything. So the winding window dimensions are this H and W. And so the winding window area, winding window, is W times H. So what would be the length of the core in this case? The length of the core is, we know that we've got 2 horizontal lengths and 2 vertical lengths. So here's your horizontal lengths, and you're going to add them up. And here's your vertical lengths. And so let's start with the vertical length on one side. So the vertical length on one side is going to be equal to H, that's the winding window height, plus we're going to go halfway into this dimension here and halfway into this dimension here. So on the top you've got A over 2, and on the bottom you've got A over 2. So it's H plus A. That's the length on one side. And then let's look at the horizontal on one side. So the horizontal on the one side is going to be the W, the winding window width. It's going to go halfway into the A dimension here and halfway into the A there. A over 2 plus A over 2, so that's W plus A. What we were trying to get at, I'm just going to show the front view of the core. This length is in the middle of the core, and so the total length is equal 2 times H plus A plus 2 times W plus A. That would be the length of the core. And we might have a situation where W equals 3 inches, L equals 3 inches. This is just an actual example that I'm trying to give you. A equals 1 inch, B equals 1.5 inches, and we're running at a current through the winding here of 2 amps, a number of turns, 20 turns. And let's find the inductance. So first of all, we need to make everything in terms of SI units. And this is, I typically wouldn't give you an exam problem where you had to do this conversion, but in a homework problem you might get it. So I've got to convert from inches to meters actually, if I want to avoid missing a decimal point or something like that. And so I'm going to say, here's what I know. 1 inch is equal to 2.54 centimeters. It's equal to 0.0254 meters. So I'm going to use the meters to make my life easy, and because I want everything in SI units. And so the H is equal to, I'm sorry, I put H and I put L up here. This is H. The H is equal to the W. So that's H. This is W. 3 inches times 0.0254 meters per inch. So 3 times 0.0254 is 0.076 meters. The A value, which is the distance across here, is 1 inch. So that's going to be 1 times 0.0254 meters per inch, or 0.0254. So I can now find the total length of the core. It's going to be equal to 2 times, so really the fact is that my A's and my W, my H's are all the same. Makes things easy for me, but I've got 0.076 plus 0.0254 plus the same thing over again. That may not always be the case, but it's the case here. And so my total length is, I think I've got this right, but I've got 0.4 meters. It's a pretty big, that's a long length. That's about 18 inches if you spread it all out. Now the area of the core is important to me also. That would be A times B. B is 1.5 inches, or in centimeters, it's equal to 1.5 times 0.0254. So that's 1.5. That's 0.0381. So the product of these two guys is 0.0254 times 0.0381. So 9.7 e to the negative 4 meters squared. Okay, and now I've got all of these things that I need. I've got my length of the core, and I have my area of the core. My turns, if I go back here, was right here, 20 turns. I have 2 amps in that. Right now, what I didn't give you was I didn't give you the magnetic permeability of the core. Typically, if we're going to have typically a BH curve that looks like something like this. So this is H and this is B. And there is, we would want to know, okay, what is the point at which we're operating on this BH curve? So this curve here would be provided. And if we also would need to know what is the permeability, the relative permeability. So the slope of the line, depending on where you're at, if you're here, it would be this slope. If you're here, it would be this slope. That is the product of the relative permeability times the permeability of air. Now, to make life easy for ourselves right now, I'm going to say, I'm just going to give you a permeability number. I'll just say that mu r is equal to 5,000. And so the mu naught, we know, is 4 pi times 10 to the negative 7th. The reluctance of the core is the length of the core over mu r mu naught times the area of the core. So we know that our length of the core is 0.4, Our permeability is 5,000, the relative permeability. The air is 4 pi times 10 to the negative 7th. And the area of the core is 9.7 e to the negative 4. So the reluctance of this is 0.4 divided by 5,000 times 4 times pi e to the negative 7th times 9.7 e to the negative 4. And so that is 4 point, it's comes out to be equal to 65,631. Now notice I didn't even use the current here at all, because I told you where you're operating. We can do some other examples where we find the B, and then we would have to know the current. But I can already find the inductance here. The inductance is going to be n squared divided by this reluctance value, 631. So that's going to be, we had 30 turns, I believe, right? 20 turns. 20 squared over 65,631 is 6.1 millihenries. So there's your inductance right there. Any questions on that? This gives you an example. Everybody's still there, I'm assuming. Okay. Now let's go.
Yeah.
Yeah, go ahead.
Yeah, no, that makes sense. It's a good example. Thank you.
Sure. Okay, here's one with an air gap. Now, I kind of have to rush through because we don't have time for this. But we could notice this problem. Maybe what I'll do is I'll record my the solution and put it in the notes. I mean, put it up on the recorded lecture. In this case, we're given the gap flux density. We're given the current. And I'm going to do this as an example that we could work out. I want to move on to this problem here. You remember that I showed you this in the last lecture. This was a different type of a gap structure. And in this case, I want to look at this a little bit differently. And I want to say, okay, let's assume that we're going to add a coil to this and put another coil on there. What would we do in that case? If we were, if you recall, we looked at this problem last time and we assumed if the mu relative was nearly infinite, then these two gaps define the reluctances, and the equivalent reluctance of the core was the parallel combination, reluctance 1, reluctance 2 over reluctance 1 plus reluctance 2. So I'm going to now think about adding another coil to one of these legs. So I'm going to put the current, I'm going to wrap it in the same direction. So in a sense, this is going to create a flux that, if it is excited, would oppose the flux created by the first coil. I'm going to say this is I2. And really there's a flux that's created by that current. If that was the only coil, it would go up across gap 1, and then it would split across gap 2 and the non-gapped leg. And we could even say, well, the flux in this would be a phi2. Whereas when we had the first coil, we could say it was I1. This would have created a flux through that would divide up between the two gapped cores. And that, I would say, was flux 1. What we have is, in general, if you have a flux linkage term, I'm going to say N, and I'm going to give it two subscripts, X and Y. It's any flux in general is going to be the flux that links into coil X due to the flux Y. So a flux linkage is linking into a coil. So let's say that I have I1 equal to some current I, and I2 equals 0. There's no other flux. There's no current in the second coil. Then what I would have done is that this current would lead to a flux 1. And the flux that links flux 1 into coil 1 would be lambda 1, 1. And this would be defined as a self flux linkage. The linking of the flux onto itself caused by that coil, that would be N1 times phi1. But because I have another coil present, I can also link a flux into that coil, and that would be lambda 2, 1. That would be the flux linking coil 2 due to the flux from coil 1. And this is what would be called a mutual flux linkage. I could go on to say, let's say I1 equals 0 and I2 is equal to some current I. And I could have been I'm just making this as a general and putting a current into there right now. Then I could say that the flux that links coil 2 into itself is lambda 2, 2. And that would be the coil 2 turns times the flux from coil 2. That would be coil 2 self-flux linkage. And I could have the flux linking coil 2 from the flux linking coil 1 from the flux of coil 2. That would be N1 times flux 2, and that would be the coil 1 mutual flux linkage. So if I have made these definitions this way, I have a lambda 1, 1, which is N1 flux 1. I could come up with a self-inductance L11, which would be N1 V1 divided by the current that is in coil 1. So there's my self-flux linkage. I could come up with a mutual flux linkage for the same coil excitation scenario. That would be a lambda 2, 1, N2 V1. That would be L21 is N2 V1 divided by I1. Now I can do the same for the excitation of the other coil. Lambda 2, 2 is N2 Phi2. That is L22 N2 Phi2 divided by I2. And lambda 1, 2 is N1 Phi2 divided by I2. So there are mutual and self flux linkages if you have more than one coil. And we could even write a matrix now. This is what I was starting to do, and I could call it lambda 1, lambda 2. This is how it helps me remember things. The lambda 1 flux linkage is going to be the L11 L12 L21 L22 times the currents I1 and I2. So lambda 1, that's the total flux linkage of coil 1, consists of a self-flux linkage and a mutual flux linkage. And the total flux of coil 2 is the self-flux linkage also plus a mutual flux linkage, and that's I1. And it will always generally be the case that these two are equal to each other. We have a homework problem that gives you a very strange situation that you can work out and derive all of these inductances. Do you have any questions about that so far? So in the notes here, I have worked out the steps here for doing this, for this two-winding structure. Now the key here is, and this is where it gets a little bit, there's some work, you just have to go through it. What if it's saturated? We can't ignore the core itself. We just have a more complicated core structure. So this circuit that I'm showing here to the left, this one here, assumes we're unsaturated. But if we're saturated, we're going to have a core reluctance due to the left-hand side of the core. I'll call this reluctance LH. That's due to this part here. We've got a core reluctance in branch 1. I could call this RB1. We have the gap reluctance, R1, is what we already were calling it. We have another branch, 2, the reluctance of the core in branch 2, the reluctance of the gap in 2. Now what I'm showing is this is for I equals I1 equals some current I, and I2 equals 0. And what you want to do is you want to find these problems by superposition. And so you're going to take this total flux here, find the total flux. This is N1, I1. And then calculate the flux in each branch. And then you know what, how would you, does anybody know if you, so you find the total flux, I need to find, so the total flux is phi. If I want to find L21, I need to find the flux in branch 1. Let me make this, instead of calling this phi 1 and phi 2, I'm going to call this phi branch 1 and phi branch 2. The coil is going to end up, it's sitting right here. I'm not showing it in the circuit, but I can still find the inductance, the mutual inductance to that coil by finding the flux in its branch. So I really have to find this phi B1. Okay, how would I find phi B1? Question. Somebody answer that for us.
Wouldn't we just, isn't it kind of like current? So we take the reluctance and split it up into two different ones, or take the...
Right. You mean a current division, right?
Yeah.
That's right. We would do a current divider. Phi B1 would be the total flux times the total reluctance in branch 2, right? Over the sum of all these, RB1 plus R1 plus RB2 plus R2. There, now you got the flux. Now you've got that flux, you would say, okay, the flux linking the flux from coil 1 into coil 2 is the number of turns in coil 2 times the flux in branch 1. And the mutual inductance would be whatever you get here divided by the current. Okay, those are the basic steps that you have to take. I'm sorry we can't go in more detail. It seems like when we do these recorded lectures, it's kind of like the clock goes on in accelerated mode. It's just crazy, okay? I think this is all I can give you on this right now. I'm going to record an example, a couple of examples just to help you. we're going to go on to excitation, AC excitation. And what we're going to do is we are going to say, what if I put an AC current now into a coil? What is that going to do? And so we're going to segue into a different situation. I got, again, a non-gapped core. And this is a typical test setup for characterizing, for generating this curve, the H curve. And what I'm going to do is imagine what you're really doing is you're applying a voltage that is variable to this coil. And the coil has resistance and it has inductance. And so that is going to limit the current through the coil. And if I put just a little bit of voltage into this coil, I'm going to show you here that, let's say that I put a point of current, a little bit of current here, it's going to give me this H value by Ampere's law in the core. And really what that is H by Ampere's law is the number of turns times the current divided by the length of the core. And that's in ampere turns per meter. I would then measure a voltage across another coil that is getting induced by this AC flux. Now what that is this. I have an AC flux, and the only difference from what we've been talking about is a scalar flux so far is when I have an AC flux, I have a sine wave flux excitation. And because of the sine wave flux excitation, it's going to have some peak flux value times some sine or cosine, you could use either one, representation of how the flux varies with time. And then this omega here is equal to 2 pi times the electrical frequency, or as we were talking about in the very first module, 2 pi times Fe. And so if I'm doing that, then by Faraday's law, the E induced is the derivative, time derivative of the flux linkage, which is now time varying. That's the same as saying d dt times n times this time varying flux. Dang it. Sorry. Okay. And this is the time varying flux right here. So that's the same as saying n times d dt of that flux here. And since it's a sinusoidal, if you take the derivative of a sine, omega t, of course you're going to get this. You're going to get a cosine, and then the omega is going to be on the outside. And so this is actually represented as some Emax, that's a voltage, induced voltage, peak. I wouldn't call this max, I would call it peak. I really don't like this term. I would call this peak. And so I've got E peak is omega n phi peak. And I also know that the phi peak is equal to the B peak, so there could be a flux density having a peak value, and you can actually think of the fact that there is a flux density that is time varying as well as a flux. They're just proportional to each other, multiplying it times the core area. And so if you know what the peak voltage is, E peak, it's equal to 2 pi F electrical times the area of the core times the peak flux density of a sinusoidally varying flux density. The RMS, which is what you'd measure from a meter, is going to be E peak divided by square root of 2. And then that's this expression up here. Square root of 2 pi Fe, number of turns times the area core times the value of flux density that you're sitting at. So this is an extremely important equation that you would want to have in your notes. Because of that equation, if we apply a sinusoidally varying current to the core, we're going to get a sinusoidally varying voltage across another coil on that core that's induced into that coil. And you could go and look at this problem in terms of lambda 1,1, lambda 2,2, and all that also, and come up with similar results. But measuring this voltage across this open circuited coil gives us a value of RMS voltage value that is proportional to the flux density in the core. And I can tell, I'm sorry, it is just taking me longer than I thought to get through everything. And maybe I shouldn't review. I think I'm reviewing too long what we talk about in the prior class. So unfortunately, we are going to end up going over one lecture, and I'm going to have to figure out how to make this up. And we will have to have the homework due on a week from today. But the new homework I'm going to post on Thursday. So, because we won't have covered everything. So anyways, any questions as we're ending this lecture?
If you're going to post up examples, could you put those up separately from the posting of the lecture that we've already gone through?
Yes, I'll do that.
Thank you.
That would be easier for me too. Yeah, so I'm going to post this lecture, and then I will post some examples of the inductance calculation, and we'll be all set to talk about magnetic core analysis with an AC excitation and finish off, and then we'll see what we can get done the next time. But we'll be 1 to a half a lecture behind. Any other questions?
So you go
ahead.
first. Sorry.
Oh, I was going to ask about the homework. So you're saying that the homework that is due for this Thursday is going to be pushed back?
Yeah.
To next Tuesday?
Right. I'll make
Okay.
it Tuesday.
Okay. That's the question I was going to ask too, just to clarify. So that's good. Sounds good.
Yeah, because I want to show you, get through this AC example, and a very rudimentary magnet example.
Yeah, that was the one. Like, I was going through the homework the other day. I'm like, I don't know how to. Like, we haven't gone over this, so that would be helpful. And then, yeah, that makes sense. And yeah, so I get that. So.
And then we're going to naturally segue into module 3 from here, because we go right into a circuit that looks very much like this one. This is a transformer too. I mean, it's and yeah, so it's very similar.
Yep. Sounds good, Professor. Thank you.
Okay, well, thank you, everybody, and have a good couple days. We had 16 people. I'm very concerned about our attendance. So, but what can we do? Anyway, we'll talk to you all on Thursday then, and I'll stay online until people are done asking me if anybody has any additional questions.
Thank you. Have a good one.
Yeah.